Okay, I think maybe we'll start. Um, okay, we start. Okay, say this. I'm no expert on reinforcement learning, so I I will first make that confession. So I've kind of crammed. I've spent the last couple of weeks trying to read some stuff and also pick KV's sir's brain and try to get as much out of it so I can give you some overview. Maybe some of you have already taken. Is there anybody that has taken here course on reinforcement? I think that's going to be offered next semester, I think. Okay, so then, I mean, I was hoping that Diganta would be there. Diganta and Shauryam. I mean, I was hoping they'll be here. They have taken the lecture, so they would probably have, if you're there, that they would have kept me a little bit more honest, and they could have probably clarified certain things. So I've, since I had only two things, there is this book, okay, which is not easy to read in 2 weeks. So I kind of looked at lots of other resources. There are tons of resources that are available, okay, online lectures and so on. Like some of them are shitty, and some of them usually when you want to go a little bit more in detail and try to understand why, so they don't. But some of them were good. So I've used a couple of those resources, and yeah, and try to make sense out of what the thing is. So the whole idea is to give just an overview. I don't think, because there are two papers, the next two lectures, one by Shauryam and the other one by Arpan. They'll be on RL. Okay, come on in. And so I thought that since there is a thing, so I might as well cover a little bit of reinforcement learning. Neither of those two papers requires you to be kind of know the in and out. But still, it would make, those papers would make more sense if you had some idea. So that is the purpose of this. The one that Shauryam is going to cover, that paper is going to talk about, is almost treats the RL framework as a black box, pretty much. Okay, um, uh, but his paper is an application. So Shauryam's paper is, what is it that you can verify about RL models? Okay, so that's what makes it interesting, unlike DNN verification. Towards the end of this, the last slide I have, but he will talk more about that. So you could treat the RL as a black box in his paper, but for him, it's more an application of RL2, what I consider as a non-traditional. Most RLs, I mean, game playing and the various other kinds of things, robot walking and things are there. But he's going to be talking about testing using RL for debugging, testing of distributed systems, and there, some of the concepts, what are the basic concepts would be useful. Now, something similar, reinforcement, because there were two papers, I just wanted to cover that. Now, for example, you'll be talking about CNN. I mean, ideally, we would have liked to have had some variants of DNN, like CNN, and someone is talking about covering recurrent neural network, U. Okay, you will see that you will have to introduce very briefly, because both those things are probably not going to be that difficult to introduce, that complicated to use, as opposed to reinforcement learning, which is like a subject in itself, and that's why I took it upon myself to do that. But the verification of reinforcement learning has something common to verifying recurrent neural networks. So, pay attention to that, because there could be some overlaps. Okay. So as I go along, I also list the references that I have used. Okay. But I'm sure there are other references, so I have put them in here, and you can search them. Okay, so I don't know. I mean, this is too small. Okay, I hope you can read it. If you want, you can come in. So this is one of the books. Okay, this is like I think it's close to a classic book. I mean, a lot of them use it, and the course here that is going to be taught next semester uses this as a thing. I'll read out. Okay, reinforcement learning is learning what to do, how to map situations to actions so as to maximize a numerical reward signal. The learner is not told which actions to take, okay, on the system that that the agent is trying to control, but instead must discover which actions yield the most reward, okay, over the long term. That is what makes this thing hard. So that is actually a quote inside in the introduction in that book. Okay, so I mean, the classic application is games like Atari or lots of other games. So typically they have large number of states and lots of actions that you can actually perform. And the world, in which case the game, here the domain is that they typically call as an environment here. So the agent is trying to control the environment. The environment is actually the game here. So it's you don't know. You only have partial information or no information at all about that. There are some things that you know. I mean, if you're playing games, you know what the rules of the games are and things like that. But you don't know what are the moves that you have to make in order to be a winner in the thing. Uncertainty over how short-term actions pay off in the long run. Okay, so maybe some things look bad now, but maybe that's what you will have to do to eventually be a winner. Now there are engineering applications as well, more and more. Okay, and one of the things with that faces that can be viewed, okay, their solution to them can be viewed in this in this way. Okay, some of you might have taken game theory. Okay, so that's also a general framework. I feel like there is some relationship between reinforcement learning and games. And games also nowadays are very extensively used for to even rethink solutions to classical problem solving in computer science. Okay, so this is one that he'll be talking about. That's why, complex control system. Okay, this is one very classically reinforcement learning is applied to make robots walk or to drive cars autonomously and so on. So that their RL is certainly used. Now, one of the new applications that are being looked at is testing concurrent systems, where you want to explore the state space. Okay, concurrent programs and distributed systems are very hard to verify. Okay, you've seen, some, insight into how you could apply to software program, sequential program verification. So the state space, the possible states, okay, that you have to encounter, and the number of interleavings kind of actions when you have multiple processes, multiple threads, etc. Very soon will the number of states that you explore become very huge, and therefore, even formal verification techniques in theory, they can cover the whole space, but they don't scale. And even testing hits a bottleneck, and there people are using to get as much coverage, okay, over it, to try and learn those corners where there are bugs and so on. So that is the idea there, and makes a very interesting application. Okay. How is it different from the feed-forward learning that you get out of feed-forward network? See, I mean, feed-forward networks, basically they work on huge data sets, okay, maybe unstructured, but there is some, and you have to organize them into some features. You have to learn about certain common things in those data set, and then those different sets of features, and finally you have to label them, okay, classify them into some finite set of labels, so image recognition and those kinds of things. So in that sense, they work on huge data set, but it's somewhat what I call is, it is static in the sense there's an input, a huge set of things, and then you have to classify them as things, and that's it's processing that huge data set. So whereas here, the goal is, first of all, you're analyzing, learning about sequence of actions that you have to perform on some environment, okay, about which you may only have partial information. Therefore, similarly, the properties that are to be verified are about the dynamic behavior of this closed loop system, which has the agent and the environment that it is controlling by selecting these sequence of actions. And they are about not just the current snapshot of the thing, but rather over multiple snapshots of states. That's why I call it as traces of states that you get over performing sequence of actions, possibly in some cases infinite in these kinds of application. Maybe the state space can be infinite, and therefore you could never know the bound at which you can find a bug. So that is the thing. So by the way, so as I go along, I'm acknowledging these resources. So this one is an ebook that I found, okay, that is actually put out by MathWork, okay, because MathWork is a fairly well-known EDA company that develops lots of tools, even including formal verification tools. They do have state-of-the-art formal verification tools, and they have these examples that I've shown here are picked from there. And I think if you want to get a very quick introduction to what it is about at a very high level, I found that thing quite interesting. So here is the maze kind of thing that is a classical thing. So the idea is to go and then to this destination square. And of course, there are obstacles along the way here. Of course, if you, the actions here are, the state is just the location of where the agent is, and this is what thing. And here, every action, the actions are moving left, right, top, top down. Okay, every action causes a change of state. Obviously, the location, you move. And the assumption here is if you try to move left when you're at the edge of this square, you remain in the same thing. And similarly here, when you try to, you can't move into the black square. And usually the game is set up in such a way that you for each action that you take, the agent is given a reward. Okay. Which is an indication of how good a move, the current move it is. So here the assumption is that for actions in every state except this one, for any action, the reward is just -1. Okay, that's how it is set. The idea is that but what you want to optimize through, what you want to find out is the optimal sequence of actions that can take you to your destination. So for example, here, this sequence of actions moves that take you from here. If you follow this route, that's the one that gives you the biggest reward, okay, because there'll be -1, -1, -1, and then you add this. Now if you do something like this and so on, the goal is to find out that the optimal sequence of moves that the agent can take to maximize the eventual reward that the cumulative future expected reward, okay, that the agent gets. Okay, so that's the so this is so if you throw away those details of what the what makes the environment, there is an environment, okay, that's the state that you're trying to control, that the agent is trying to control through set of actions. Okay, and I mean, to actually determine what action that has to be taken in a current state, you have the environment. You can perform the action on the environment. So the environment is available for simulation and so on. Obviously, when the action is done, the environment changes its state. But the agent only has partial information about. It doesn't know about the complete state of the thing. Otherwise, this person itself could be the agent. So in determining the future actions that he takes, in that sense, is what I say it is unknown. Okay. You look puzzled? Yeah. It doesn't have to be. I mean, what doesn't have to be? Indeed? What is, yeah, in that example, the state itself was the position. Okay, so that was, so that was available. But in general, I'm saying that's a simplistic thing. Okay, so where you may not know anything about the thing or very little about the actual state. So in general, you are allowed to observe only a partial. You make partial observations about the state. Okay, so there is a state space of the environment, and then actions are when performed on the environment, they map a state to a current state to a new state. And the only thing that the agent knows about how, as a result of performing that, is this reward, which is a real valued number that the environment that she gets from the environment. Okay, to determine how good it was. That's a local reward. A policy is something that maps a state. Okay, so it could be the initial state to an action, the one that needs to be performed. Okay. So an optimal policy, see, this is actions. An optimal policy is given, this should be a state I as well, okay, not an A. By star chooses actions to maximize the cumulative return. Okay. So, and the problem of reinforcement learning is how do you construct or synthesize that optimal policy, yeah, which is to maximize the reward. The policy function tells you, it determines in each state what action the agent can perform. The agent usually has a choice. No. The agent chooses one action, okay? This is a set of actions that are possible. At any particular point, the person chooses an action. That agent may have a choice of several actions, but any particular... Correct, yes. And that, no. See, yeah, the pi star, okay, now there is a power set of policy functions, one of which is pi star, okay, which is all, here I'm defining what actions. If you know the full expected reward, all the way to the future, you know what the thing is. The idea is to learn about the action that you that you could perform, that you can perform, so that your return will be optimal. Okay, and that particular policy function among all the policy functions that are possible in each thing is what is what I call as what is defined as an optimal policy. Yeah. Yeah, I mean, I think I can skip this slide, but I'll come back to this, thing. I mean, this is, uh, yeah. So reinforcement learning can be expressed as an optimization problem in a dynamic programming framework. Okay, so that's typically the method. Maybe there are other methods in control systems, for example. This has been a problem that they've been looking for ages. Okay, and they use different kind of techniques more directly. But here, most reinforcement learning methods are where the solution of the method is expressed. The problem itself is expressed as a dynamic programming problem. For people in computer science, okay, maybe you don't call it dynamic programming, but recursively, when you do things, solve things recursively, that's what in a naturally dynamic programming is. Traveling salesman problem, Fibonacci number computation, all of them are expressed as, if you want to solve something, I try to solve smaller problems, and then I put them together. Okay, the traveling salesman is very much like in what I call as dynamic. If you want to find the optimal route from here to there, you have to figure out, move to something that has a location which itself has an optimal route from there to the thing, and so on. But let's try to now this slide very quickly formalizes all the concepts. Okay, the thing that I introduced thing. So this is what is the objective function that your RL problem is trying to optimize. Okay, I call it optimal policy, and this is the objective function that it is. So this is given a state, and this is a sequence of actions. Okay, t going from 0, 1 to maybe some bounds or some infinity, possibly infinity. So it has to optimize this expected reward. Okay, there's a gamma that is thrown in there. What is that? Okay, so I mean, if you execute this, as I said, in each step, you get a reward, and what you want to emphasize, the expected reward is just the sum of all the rewards that you get. What the thing is, and that is actually the expected reward. Usually, this expected thing has a what is called a discount factor. Okay, because there you could whether you want to bias it towards you apply more weight to what the future rewards that you get as opposed to the current the current reward. So you can, this is kind of a tunable parameter, hyper parameter in this optimization function. You can choose gamma between 0 and 1. So yeah, if it is 0, if it is 1, then you give lot of weight to your future reward, and you emphasize the current reward. So that is something that you can actually control, and therefore the expected reward that you have to your problem has to optimize is usually expressed in this in this fashion. So this is for a given sequence of actions, and S, this is how it is defined. So this is pretty easy to understand. And when expressed as a function of a particular state, okay, among all the sequence of actions that are possible from a particular state, this V star of S expresses the one that optimizes over all sequences of actions that we perform. So that is obviously, one that over all AT, all sequences, it gets the maximum of this. Oh goodness. Yeah, this is maximum over all sequences. This is correct. Yeah, over all sequences, infinite sequences, you compute, apply that to get the expected reward on that. And, so V star gives you in that state the maximum reward possible, okay? The most optimal reward possible, okay? Now here, this solution, I mean, this problem now is being expressed as a dynamic programming problem, or as a solution. I try to call it, would like to call it as a solution to a recursive equation, because I'm familiar with that. Okay, abstract interpretation, that we have talked about, computing inductive invariant, they're all solutions to recursive equations. Okay, so here, that is what it is being expressed here. So you see, V star is being defined in terms of V star itself. Okay, this is over an infinite, potentially infinite sequences. Okay, so it is good as expressing as a problem. So here, what I'm saying is you take as this description. This is once again, I accepted it from that book. So it says that you can always express the optimal value in a particular state in terms of what you, in terms of the optimal value of the next state that you can possibly take from the current state. Okay, and if you already know this for the next state, okay, then all you need to do is to then in order to find out what is the maximum thing possible, then you will have to take the maximum reward in the maximum reward, that action that gives you the maximum reward in the current current state. Okay, it doesn't mean that the action that gives you the maximum reward in the current state is the actual optimal thing, because that depends on what the value, the optimal value of the next state is, because different actions can yield different, can push the environment into a different state. Therefore, so there is that thing there. Yeah. 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 T is the what I call as transition function. Okay, so here I'm assuming it to be deterministic. Okay, the environment to be deterministic, which is not the case at all. Okay, in general, for simplicity, I'm assuming. So given a state, it gives the next state, because it's deterministic. I'm using it as a function here. Okay, but if it is non-deterministic, then you define it as a relation. Okay, so where it can relate S and S prime. Typically, especially when you don't know, when you abstract the environment, you only have partial information, you have to allow for the possibility that it can take, they can have moved to multiple states. Okay, probabilistically. Okay, because even that information. Therefore, the environment T itself is usually defined as what are called a Markov decision process. Okay, in which not only the same action can result in different states in a probabilistic fashion. But to understand these equations more easily, I'm making this assumption, but you can get a more general version of this. Yeah. Yeah. So V star of S, this is what I'm kind of expanding it into this. So over all the next states, which is what I explained in words, okay, over all the next successor states that are possible as a result of taking various actions that are enabled, that are possible for you to take, you have to take that thing. Yeah. No, that's not square. That's just it's a reference to a footnote. Sorry, this is a where here. This has nothing to do with that part of the thing. Okay. Now, then you can also express. Now, if you know this function, so expressive dynamic programming DP problem is V star is your thing is you have to solve somehow this recursive equation. It's actually the problem of synthesizing loop invariance, okay? So the T, it takes the current set of states to the possible next successor states, and you keep doing it until you fold back, okay? And that is somewhat similar. There is some analogy. So Q star, once you have V star, Q star, then you could use Q star to give that, to give a value, yeah. So given a state and a given action, you can, there's something yeah, okay. So yeah, I'm rewriting this with a A. Yeah, overall S star possible. That's all. That's all I'm, So yeah, it's with a particular A. Okay. Here I was doing it max over all A's. This is given an A. It gives what your reward, cumulative reward is, the optimal cumulative reward is when you take that particular action from there. And the reason that this Q star is involved because that is just this itself does not give you a way of selecting the action. But if you had this function which gives a score to each of these actions, that's how it is thing, and then you can use that score to do. See, in order to solve this, unless you use fixed point solving methods that are used for a thing, that is kind of thing is not possible here because of continuous nature of the states and so on. So most methods, they use some kind of an estimation. They estimate things, get better and better estimates to this V star and Q star function. Okay, so and if you don't end up solving the whole thing, then given this score, if you can somehow compute this function, which gives a score to the optimal reward that you get as a result of performing particular actions, then you can, and this could be some probability, especially if you have this, stochastic thing that can give you a thing, then you can use one of, multiple methods, okay, to select which action to perform. So for example, you can use this softmax function, or you can, you can use some random method, okay, for selecting the action. Sometimes with some probability epsilon that you use, or you can use based on this estimated optimal value that Q star gives you. Okay, this is one strategy, and there are lots of other strategies here as well. You will notice that the larger the value of this, this gives the probability. This gives like a probability, and then you can use that as the distribution to select, okay, according to that probability distribution determined by that one. In this case, it is the probability is kind of pre-determined, chosen with respect to size. So there are, those different strategies, but usually the RL, solutions to RL really it would be to get a very good estimate, if not the actual optimal policy, something very close to that, to Q star. Okay, so this is just, yeah, so all the things that we have introduced, I'm trying to define them as, in some cases, as formulas or programs. So for this here, the state is position, the full complete state is the position of the agent in the grid, and the color, okay, because that's also determines, okay, which way, what the next state is, and I'm assuming that it is numbered 0 through 24. in order of that thing. And then the action is moving left, right, down, or up. Um, and the reward is, if it is blue, it is so on. You can define it. And initial state is something as shown there, and you can define the transition relation. Okay, so here this transition relation captures the environment, which is this grid here, completely. Okay, but you don't in general what might be available to determine that Q star might be only a partial observation of the whole state. And now, you can compute, given this, because it's a finite state with finite number of actions here, you can actually compute all the expected rewards that you get from each of the, for all the sequence of actions that you can actually perform. And since the goal here is to just reach this, then you can actually do this. And here I'm computing it for finite sequences. Of course, you can imagine that you're here and then stupidly turn, keep moving left and so on. And then if you keep moving left, then you just get stuck there. Okay, never move the thing. So in that case, you will get your cumulative reward will be minus infinity. Okay, and so on. So, but usually in these game-like scenarios, you are interested in looking at unbounded, optimal policies over finite but indefinite lengths of sequences that maximize your expected reward. Yeah. So far, any questions? Okay. Okay. Yeah, these are some theoretical questions. Okay, that kind of occurred to me, and I think I haven't looked at the literature. I'm sure all these things are none of these is open. Probably they're all solved. Does the Bellman equation does it always have a converging solution in the limit? Okay, I mean, even before you can ask the question whether I can always, is there a method to compute that optimal reward for each state? Does it even converge into a limit? And I think it does, especially because of this gamma. Okay, because you keep on, each time you're taking gamma to the I, and therefore it keeps decreasing, even though the rewards can be negative and positive, and may they flip between the two. And I think you can argue each time, even if it flips, you'll be reducing it, and therefore finally it has to converge. But what is less obvious is if there are analytical methods to actually, methods means procedures, I'm saying algorithms, okay, to compute those things. But apparently there are, even when they are infinite. Obviously, if you're only looking over finite sequences, then then they do terminate. But over infinite domain, whether it does or not, the thing, under certain conditions, they do exist. Okay, so now quickly, this is just the same questions repeated. Maybe that book that I showed you has some theoretical results of this kind, and that I can do. And I have not looked at, but I have consulted with some of the people, and then that I know that there are things, even if you want to use that infinite series and methods, which will not be practical for you to do. That's why I said this is a theoretical question. Okay. Now, quickly, I'll come to one of the more popular methods. I don't know what the exhaustive set of methods, that learning-based methods that are that exist to solve them, but Q-learning is certainly one that is very widely used, and that's why I'm summarizing, giving a summary of that. Yeah, forget about this MDP. Okay, MDP requires probability, then you'll have to sum over the probability, so that I'm not showing. But what I'm saying here is either environment only, some part of it is known or nothing is known. For the moment, say you don't know anything about it, okay? you know its existence. There is an environment. When you query, when you make an action, you know what the next state it gives you and the reward it does. But I don't know anything about it to be making to guess about future rewards and so on. So what it does is this Q learning, it adaptively learns that optimal Q star function, which tells me which action to do in a particular state to get to construct an optimal policy by adaptively learns from a history of interactions. Okay, there is history of doing actions in interactions for doing actions between the agent and the environment. So one way to do that is to represent the Q function as a table. I mean, if it's very huge, which usually is the case, then it could be hashed. So the table, it gives a value for every pair of state action pair. Now, what this does is it starts with it iteratively basically estimates, it makes better and better estimates of Q star by looking at lots of interactions, history of interactions that by history I mean sequences of states that you get if you were to perform some interaction. So at each iteration I with the environment, the state Si that you get, let AI plus 1 be the action that is selected based on the current the Q value. Okay, the value for that pair Si AI plus 1. Okay, AI plus 1 is one of the actions that are possible, and it updates Q as per this update rule. So this is the current value. It updates with this term. So what are the various parts of that? Okay, obviously this is the reward that it gets, okay, as a result of performing action AI plus 1 in SI. Now you have to, what is it that you increase it by? Now, okay, so this one, both these are obtained by actual simulation of the environment, okay? The next state that you get, the actual next state, and the reward that is determined by the actually performing the thing. And then, you have to, then you see what the, this is kind of the discounted optimal future reward among all the SI plus 1 is the new state that you get, okay, as a result of performing the action that you have chosen, which is chosen as per the Q table. Q table you choose only by the current thing, and then you perform as a result of, so it's you kind of doing one more step and then seeing what the optimal future reward might be, one step future reward might be, and how far that reward is from the current value. Okay, so you're taking the maximum, of course discounted by some factor gamma, and then you subtract that thing. Why do you subtract? And that subtraction gives the error of the current estimate from the new value. Okay, this is a way of looking at, you can only do it, I mean, this is doing it incrementally, okay, one, by looking at future reward, one step at a time. And this is how it is. So this is the difference. If you want to exploit this particular maximal value among all the actions that are possible from the next state, then you better, increase this by that much, because as a result of taking AI plus 1, there is potentially you can increase your thing by this much. Okay, the max you can actually get as far to that, and that you will, okay, so you could take the whole thing, that the complete error, how far that thing is from the optimal value can be added to your thing. So that will make a better estimate. Or it is multiplied, just like gamma, there is a learning factor. How, whether you do it aggressively. So this is trying to learn what the estimate, make the current estimate better by looking at future rewards one step at a time. Now, whether you want to go full hog and then put all the effort in the learning, or you want to nudge it slowly, okay? That is what is determined by alpha. It's because you don't know right now, okay? Because if you knew the entire future up to the limit, then you didn't have to do this, okay? Maybe that there is something that some other thing that might give you better future reward, and that's why. So you can choose how much you want to put your trust in your the learning factor, and that's why it's called the learning factor. So, and that's how it is. If you see, if I put alpha to be 0, then you're not learning anything. Okay, you're stuck with what the current Q value is. So you're not improving anything at all. If it is alpha is equal to 1, then you are incrementing it or whatever. Okay, if it's a penalty, you're decrementing it, but it's just the maximal thing, and then that's so you control using that. Okay, like I said here, this by state, I've given the state, but the state could be some they can be a function which extracts only, looks at part of the state as well, not necessarily the entire state. There is also this thing here. I've shown it as though that you are updating Q table and by learning after every step, but usually that's not how it is done. What they do is they simulate in the current state based on the current Q table, pick a sequence of actions based on the current Q value, simulate it over the entire sequence, and then do update the Q table at multiple points. I'll show you an example. That is a very simple example that it is, and that is how it is done, rather than incrementally updating it at every step. Now, I have thought about it, but I don't know what the thing is. Maybe this is, you can learn more about several states in the same in the same step. Okay, so that choice is sometimes used as well. So let's see how Q learning works on this example. This is a much simpler example than thing. Once again, this one is borrowed from that ebook. So it's a simple thing, okay? Goal is to maximize thing by moving as quickly as you can to this state S3. So episode is a sequence of steps, okay? So you normally, you simulate over the, over a number of steps as long as what episode decides. Okay, so this is, you start by initializing it to 0, all the Q value. The rewards are shown here. Okay, reward of moving, taking this action to move here, you get a reward of -1. From here, if you move to the right, you get a reward of +10. That's how you have to read this. Okay. If you try to move left, you stay there, then you get a reward of -1. So you start in episode 1, you do 2 steps. Each episode has 2 steps, here. That's the assumption. So now what action do you take? You can move left or right, only left or right here. I mean, the strategy that we're using is that something similar to the epsilon greedy strategy, okay? So here, if you have, if the Q value for a particular, for multiple actions are the same, then you flip a coin, okay? So that's the strategy that is used. Otherwise, if it gives a unique maximum score for a particular action, you choose that, and that's the strategy that is used. So here both, so left or right, it gives the same Q value, and therefore you do, you make a, I randomly choose to do a right. Okay, so my reward is -1, and also the new Q value is the current Q value plus the assumption here is I'm pumping, the learning factor to be 1. So I want to learn as much from the future reward 1. Then this is the reward. This is the current Q value. This is the reward that I'm getting, -1, plus here, this is the current Q value times gamma. Gamma is assumed to be 0.9. Okay, this is actually 0.9. 0.9 times 0, okay, plus minus 0, okay, right? This is the current value. This is how you do. So, and then you subtract it, and that is, gosh, I can't read it myself here. That's the trouble I get. This is equal to -1 is what. Okay, you don't update that. I mean, you of course temporarily update, but until you finish the episode, you'll be using this the current Q table to compute all the new values. So this is the value for taking the right action. The Q value is updated for the next episode, okay, to be used. So and then similarly, if you in S2 you move to S2, okay, because you took a right. In S2 also, because the score is the same, you're doing random, then and you randomly choose right, and therefore you get 10 when you plug that thing there. Okay, so that kind of learning, it is updating the Q value to the value that, okay, if you moved right from there, that's a good thing, that you will get some good reward. So that is the end of the episode. And then you update the table, and then you, when you go to the next episode, you start from the same initial state, and then you simulate. For another episode, you compute all the new Q values as per the update rule, and you update and keep going, okay? Until you either hit your goal and you stop, that if that's the RL problem is goal oriented, or if it is open, and then you keep going until it converges, if it converges, okay? Now that's a question that I will raise, okay? The Q learning, that's the same question. I'll come to that, there's a slide. So no, there is a paper that says it does converge, okay? With that way, where the Q value, the equivalent, the analogous of the Bellman equation that is to do with the gamma, etc., that there is thing. Now, what are the conditions under which it is guaranteed to converge? I don't know. I have a paper that that is a classic, that is, I have so many references to that. That's by the people who invented the Q learning. And they have a proof there that it does converge. When you use the stable method, okay? When you use the stable method. So a similar thing is done now with this updated table. No, this is updated. No, this is the updated one, I think. Yeah, this is the updated one. Now here you will use the greedy. This is usually called exploration versus exploitation, okay? Exploration means when you ignore the Q values and then you do random action. Or if you use the Q value to pick the action, then it is called exploitation, because you're exploiting the rewards. So here, because between these two things, moving left is has a higher score. Okay, although at this point, moving left hits you into a wall. Okay, but you still do that, and then you thing, and then from here, because you already learned from the previous step, and you've improved the estimate for Q2, you will see that moving right will give you a better expected reward, and those will end up updating the Q value of 8. I mean Q value for doing an action right to 8. And now you can see that it has learned the optimal policy, which is it should be moving right. Okay, in two episode steps, or you have learnt it. Okay, so I guess at this point I will flash that slide. Okay, so this is kind of the workflow of reinforcement learning. So of course you have to have an environment, and if you want to use some partial model of your environment, you will have to model that either in MDP or deterministically or whatever. Decide what states you want to observe among the state, etc. That is a design choice that you will have to make. Okay, and then the reward functions, very critical. Okay, both these things are under you have to do it before you set up. Okay, how do you reward, and the representation that you use for your agent. Okay, this is where the Q learning, classical Q learning, uses just a Q table, and if the state space is too big, then it uses some hashing techniques to do take care of that huge state space. But another possibility is to use a free forward network for the Q table. Okay, and I have a slide as to how you could train the feed if you used it. I think because after all, a feed forward network, I mean a DNN, is a compact function approximator, and we are computing, estimating the Q table. No, that's function is what we're trying to learn. Therefore, you could say, why not represent it as a DNN? Okay, but let's assume that we are a table, and then there is a this process, the iterative process that I showed is the training phase of the thing. I mean, some RL methods have two phases. One, a training phase, where you learn the de-learning loop until it converges and terminates, or until you have explored some number of episodes. After some number of episodes, you just cut it off, and then you deploy. Okay, based on that Q table, Q function that you have learned, and then you actually start doing the thing. That is one. But there are methods. Okay, there are methods where they don't use two phase. Okay, there is only the phase one part of it. Okay, for example, in the because sometimes the phase two does not make sense, especially in testing a thing. You just have to keep on exploring. Therefore, you continue to explore until you hit either a bug in that case, or a goal. So that is also a possible way of doing it. Okay, and so there are two modes in which you could do. Okay, so some aspects of Q learning. Yeah, so these are some choices that you could make. Okay, like I already said, you have to generate point samples. How do you generate it is and how frequently, how often you update the Q table. So usually you kind of episode is the number of steps that you determine, and then you generate samples for the sequence for some length there. Update Q at multiple sample points, SJAJ, that you get as a result of by looking at the states that you get from that simulation thing. Now, if it is only so that is one. What is the termination criteria? Okay, run till it stabilizes, run till you get a goal winning state, or a fixed number of episodes. All this are possible, and there are some possible of what is how maybe you can combine some random with the exploitation possibility, and you can do offline versus online strategy, which I just implemented, either a two-phase strategy or the other thing. So, and there is also this thing. So this is the point that I already made. How much information do you put in? How much information do you take? I mean, use for the environment. Either, so that's when, if you don't assume anything, if you don't use any information about the thing, or as little, then it is usually called model-free learning. Or you could have a very approximate model of your environment, which you could use in MDP, and then so that has some partial states and partial information about the probability of which actions you take with what probability and so on. So so you can have these two um, approaches. Okay, so now I'm coming back to your thing. Okay, so questions about Q learning. Once again, does it terminate? Now that paper does have a result, a proof, a formal proof that it does if it is represented in as a function with certain constraints. Okay, it does. Now, but if it is done as a neural network, there is no guarantee that it'll terminate. Okay. Um, Now, these are two questions that I had. I mean, I have no answer, and I mean, I have not seen the paper. Now, does Q learning satisfy the following monotonicity property? That is it, if you're using only finite length sequences in each episode, does it, as a result of doing it, I mean, updating it, does it always, if I is greater than j, does the policy defined by QI is more optimal than policy defined by QJ, okay? And the other one is, if you're now simulating it on, I mean, I found these questions interesting, and that's why I have raised, okay? So if you are limiting your episodes to finite length of sequences, and after you have updated it over the entire episode, what you get will be, after all, that update is based on not infinitely long sequences of history, but only finite sequences of certain number. Does it, after running the Q learning for n number of sequences, does it give the optimal policy for that for all those sequences? I guess this will ensure this. I don't know if these questions are addressed. Certainly, the convergence question is addressed in this paper, and they have a proof that it does indeed terminate. That partially answers your question. I think if you want to look at as to why, you have to go look at that paper. Okay, in the final 10 minutes that I have, any questions so far? Yeah. Okay, so how does the Q learning method work if you represented the Q function, instead of representing it as a table, okay, like what I've shown, instead you use DNN? I think that's the question that you had, that they've used in the other paper, and maybe you could do. And this I found, even the book that I showed you, certain they don't have, they don't discuss how you actually use DQ, I mean, how you train the DNN. But I was able to find some references, and what I have discussing here is based on what is given in that book. Yeah, the idea I've already stated is to represent the Q function used by the agent as a feed-forward network. Let's call it DQN. Why does it make sense? Because after all, DNNs are a compact function approximator, and you have control over a lot of these weights to control their learn the thing over and so on. Can be more effectively trained on large samples, and you can use gradient descent, like you saw in the alpha crown, that they were using gradient descent itself to optimize, to find the linear upper bounds in a better fashion. So the input vectors to this DNN are vectors denoting the state action pair. Okay, for every state and for every action, that's what it is, and it gives a score. Okay, just like the previous Q table. So when you're using DNN, the questions that you should be asking are, what is the loss function? If you're using gradient descent, then here the objective function is the loss function, okay? And you are solving for the theta, the weights, to reduce that thing. And typically, like in any DNN, you what you take is that error, the error part that I showed there in that Q function. That's what you do. Okay, I've just added a theta here, just so this is the current value, and this is the distance from the optimal based on the one step reward, and then take the mean square of that. They say E comes in because if it is simulated over sequences, then you have to, there'll be a sigma that is that you will have to do. Yeah, there the square is really square, okay, not the huh? Yeah, there is a left thing missing here. Yes, you're right. Yeah. I think that's how they do for all the samples, nah? How do they do in? I think they sum it up and then they take the square. Yeah, yeah. I think the square is for the whole thing, or um, yeah, but this itself, yeah. So there will be a sigma here if this is over several steps, okay? And that's what would be the thing. So to finish up, how are okay? The other question is how are samples generated for running for training this DQN? You know, what is the loss function? This is the one that is optimized. How are the samples generated? And how often do you run? What should be the size of the sample and so on? So the idea is use the current DQN to generate finite sequences of actions from the starting state, that is episode, just like you did there in the earlier method. Now simulate the environment to generate intermediate states. This here, you actually simulate the actual environment, okay? And you use the same neural network to generate the optimal value, this one, okay? For each of the states in the sequence of things that you have generated to simulate. So each of them, that gives for each state this what the current value is and what it should be updated to if it has to get the optimal value. That is the error. You sum the error and then you take the square. The other question is how many samples. If you have looked at some methods for running gradient descent, it's not as simple as that. Okay, even with a large set of data set, they kind of divide it into batches and various things, and then they do some rigmarole, okay, for getting the best out of it. And something similar is also done here. Okay, and there are lots of details here, and they even have code how to do that, etc. And there could be variations on that as well. What is a good resource to look at all possible different ways of doing it? That would be a good thing to do. How many samples to use, and how often do you do gradient descent? So usually these are the three parameters that are kept. Episode that I've already introduced. Episode is the number of episode. Each episode has a set of, some number of steps, okay? And you can have several number of episodes, okay? Episode is the number of steps each that you do the simulation. And then there is frame, and then there is batch, okay? Each of which is a number. And the way it is done is you accumulate samples over an entire episode and store it in a buffer, okay? So which means that you generate, okay, when you simulate for an entire episode, you get a whole bunch of states, right? In that sequence. For each of them, you can compute this. this difference, and that is, you can treat that as this is the expected value, this is the actual value kind of a thing, and that's why that's the error. And then you accumulate samples over an entire episode, store it in a buffer, and after every batch, after you generate every batch number of samples, you run gradient descent on that. And you run gradient descent on it. But there is one other interesting thing that they do. Instead of using the same DNN, a single DNN to generate the samples as well as do run gradient descent on and update, sometimes they have two DNNs. Okay, one is called a main DNN and a target DNN. This target DNN is exactly a copy of the main, except that it is updated not at every step, but every so often is, and that is determined by frame. Okay. Yes. Okay. So the main DNN is used to select actions in a run, where a run is the number of steps in an episode. A run is doing all the steps in an episode. And then you run the gradient descent, which updates the theta on the mean. Target is used to get the optimal value, this one, okay? That stays the same over until over each generation of samples. And every often, once you've reached a frame is a counter that you keep coming, then you move the weights that you have learned onto the target. So just to probably introduce some randomness in this thing, so that it doesn't overfit or something. I don't know what the thing is, and that is how it is done. Okay. So here's what the final slide that I have. So yes, the paper that Shauriyam discusses will be how to verify these kinds of systems where you use RL. They're usually called learning augmented systems. Okay, so systems where the controller is replaced with a a controller that uses Q-learning to do it. So here is what I've kind of briefly said explain. Until now, when you're verifying a DNN, okay, the properties are of this fashion, okay, of this shape, of this kind. This is a stability property. You can have various other things. If you really want to look at some of the properties, by the way, one final assignment that you will have, which I'll treat it like a take-home exam. Okay, I told you I've been repeating this several times. So I'll be giving you either one or two, not very big, but something which is slightly more meaningful, more interesting than the tic-tac-toe thing, okay? And I want you to do verify that with a set of properties using Marabou, using deep poly and alpha beta count. Let's see how it goes, okay? We'll have to make that assignment as well. And then, you don't need to understand the entire internals of alpha beta count, etc. But you need to know how to use those tools. But nonetheless, all these are the shape of the properties like this. So you have a precondition on the inputs, then you have an invocation of the network, which gives some outputs, and then you have a post predicate. Typically, you take the negation of the post predicate if indeed you want to prove validity, and then and you prove unsat of that. Or there may be, your problem could be proving SAT, in which case you just take it. Anyway, so there is some property, some formula that relates a predicate, that relates the output produced by the end with X. So for example, a stability property could be something like this. If X0 is an input that has been classified with a label L. That's the assumption. Then if I change x naught into a new output such that the difference between them, these are vectors, okay? Vector difference is less than or equal to some bound perturbation. And if I run n on x and I get the output y should be the same label. So it should be stable under perturbation. That's the kind of property. Now, if you want lots of other properties, this ReluPlex paper that I've uploaded in the appendix has a whole bunch of properties, okay? Both stability and interesting properties that they have verified for this ACAS XU thing. And it might be worthwhile for you to look at them just to be curious, because when I give you the assignment, I will not formulate it for you, okay? I will give you a description of the property in English, okay? Before you feed it into one of these tools, you will have to make up the query yourself, yeah? And as you know, these some of these tools, they restrict the kind of formula that you can use for P and Q. If you're using deep poly, all of them will have to be that they're between some bounds, where the bounds are expressed as linear expressions and so on. So different tools impose some constraints on what shape, meaning that what kind of formula the P and Q can be expressed in. Whereas RL properties, like I briefly mentioned earlier at the start of the lecture, they are constraints over traces resulting from executing a learned policy on the environment. So in order to express them, not only if for the moment I'm assuming that my Q function is represented as a neural network, okay? And now I have learned, okay, in all these cases, I'm assuming that a Q function has been learned and represented as a neural network. And after that, you want to show that what the learned policy does not violate certain properties when it is actually run, when it is deployed and run with the real environment, okay? So I'm only showing the kind of properties in general. So Shauryam will actually show you for a case study when he discusses the paper with more details. So you have a learned policy. Maybe I should be putting it as pi star, initial state, and a trace that you get that gets produced by running that policy from that initial state. That is a sequence of states. Each of these states, successive states, are related by the transition relation for the actual environment. That you need to model, okay? You could model that, so that is a requirement in all these cases. You can model them as an over approximation. We've been talking about over approximation so much, okay? So, so that T has to be modeled as a formula. N has to be modeled as a formula, which you know how, okay? Now here are some of the kinds of things. Something bad never occurs, okay, in any of the, for any policy, I mean, the policy that you've learned, if you run it from N, something bad never happens, which is equal to showing that for every I greater than or equal to 0, not of bad. So bad is a predicate that you define. That's an input, okay? Something bad never happens. For example, a robot never hits an obstacle in an optimal walking policy, okay? That could be the thing. And these kinds of properties are called safety properties. And this is called usually a liveness property, where we say something good eventually happens, that there exists a state, a future state, where good of SI can happen. You don't know when that will happen, because in an optimal policy, you don't know how many steps it will take to reach its end point. So robot eventually reaches its destination in a walk within, maybe you can bound that as within 10 steps. So that will be a formula encoding a trace property now. So because of this, you see, this will have multiple invocations of the DNN, because each time, each transition is governed by the action produced by the one invocation of NNN. So that's why this kind of verification is much more complex, okay? Because in terms of complexity of the formula that you get, in terms of the number, you'll have to make multiple copies of the neural network. What I mean when I say multiple copy is not literally the neural network, but the formula that encodes the behavior of the neural network, okay? So therefore, your size of the formula that you will have to verify, if eventually you will ship it into maybe Marabou or Deep Poly or Crown, Alpha Beta Crown will be bigger. And therefore, you have to have even more sophisticated techniques to address the scalability issue. Okay, so he will be presenting one such method, a method called bounded model checking, which will show how it works. So it'll be interesting for you to know what the thing is. Okay, that's all I have. Yeah. Okay. Who's missing today? No, Sainthan is not registered, so I'm not that worried about him. 1, 2, 3, 4, 5, 7. Oh, all of you are here. That worked. Okay, thank you. Bye.